네, 한성민 씨 안녕하세요. 제 말 들리시나요? 네, 박건호 씨 안녕하세요. 제 목소리가 잘 들리시면 잘 들린다고 좀 말해주세요. 아, 네, 네, 알겠습니다. 네, 정상목 씨는 오셨나요? 네, 안녕하세요. 네, 그러면 다 오신 것 같으니 바로 시작을 하도록 하겠습니다. So first of all, I wanted to ask you whether you have any difficulties when you solve the homework number 3. So do you have any question to me about the homework number 3? Okay, I have checked that all of you, 3 of our students submitted the homework. So okay, then let's move to our next homework, homework number 4. Okay, so what we have done is now we can read a file which contains some information about certain area. So that is really discretized with a certain point. So now we can understand if we have multiple points at the boundary and inside the bulk, then the information about the triangles in it is specified by the file element file, and based upon that information now you can understand how triangles are distributed over the system. Okay, so I think that now you can read it and even visualize it, also calculate a certain coefficient for our simulation, and also now you can calculate the Laplace equation. So however, in our previous homework number 3, there was a certain limitation. What was it? The limitation was the boundary condition for directly boundary condition. So points for the boundary conditions are already given to you. So the top point and bottom point of our structure is biased as phi equal to 0 and phi equal to 1. Of course, this cannot be a general one. So what I want to do today is, instead of specifying or predefine the boundary condition points, I wanted to introduce a certain information about the contact information. So this is contact, and also contact. So how can we define the contact? Or for example, let's say this is point 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, sorry about that. 8, and I have to say this is 9, and this is, let's say, 10. Obviously, we have two different contexts. For example, one contact has vertices like number 4, vertex number 4, or why don't you just say V to say this is really vertex, and vertex number 5. That is one thing. And another one is vertex 1 and vertex 8. So now you feel that the best way to specify a contact can be just to specify the list of vertices for that terminal. For example, this is the list for that contact, or this one can be a list for the upper contact. Okay, so how about your opinion? uh, it sounds good, however, in reality, so we do not provide the information, contact information, not in this way. It is because when you specify your region, then you specify the elements like a triangle. Yes, so exclusively in this example. However, if we move to the three-dimensional case, maybe you will use the tetrahedron. So it means that instead of specifying the vertices, we prefer to describe our system or our object inside the system with certain elements. Of course, contact in this case is not a 2D material, 2D object. So in this case, region is considered as a 2D area. However, contact is described as 1D line segment. Okay, so it is much better to describe this one. For example, it means that if we expand our contact in this way, yes, now we have a lower contact and upper contact. If we follow just a list of vertices, then we have to say this is the one for the description for our lower contact. And if we have to consider our upper contact in this way, then we have to say, okay, we have additionally V2. That is enough for specifying our newly generated contact points. However, once again, this is just a way which is not frequently used. More frequently used approach is just specifying V say V4, V5, V5, V6. You know, each row specify certain line segment or an edge. So an edge is specified. This is an edge, and another edge is specified. So by summing them all, then that represents the contact. Of course, in this case, we can find that this vertex is repeated twice, but it is much better then have just a list of vertices. Then why don't you go to our top contact? In this case, we will have vertex 1, vertex 8, and vertex 1 and vertex 2. That will be the specification for our system. So now let's come back to your previous homework number 3 example. So of course today we have homework number 4. However, that will be quite easy to solve, I hope. Yes. Previously in homework number 3, you had a circle and you apply phi equal to 1 and phi equal to 0 to your system. But now, instead of that, now you have to read certain file which contains the list of edges. Then yes, there will be something like this. So how do you specify the contact points or contact edges? So please just follow the way like 3, 4 in order to specify the edge connecting vertex number 3 and vertex number 4, or of course 6, 7 that represent an edge connecting vertex number 6 and vertex number 7. Okay, this guy will be specified by this 6 and 7. So by adopting this convention, please make your Laplace solver more general. So now you can specify yes and yes the shape of your two contacts, so lower contact or top contact, or the contact where 0 value is applied and value 1 is applied. So selecting or setting the shape of those contacts is really up to you. You can freely specify it. For example, you can consider, for example, half 90 degree for your top contact and another 90 degree for your lower contact, but it really depends on your choice. Or you can test your code with many different configurations of your contacts, top contact or bottom contact, or anyhow two contact. Even you can try to apply more contacts, not just two contacts. For example, you can apply -1, then maybe you will have a very interesting result over your system. Okay, so do you have any question on homework number 4? So this is the first one for homework number 4. I think that since all of you have successfully completed the homework number 3, the capability is already there. So what you have to do is just to introduce additional routine to read certain files for top contact or ground contact and excitation contact. Read two files for two contacts. Of course, the file name can be specified you, so you can set the contact file name and read edge information. And from that edge information, you can apply the directly boundary condition to that, so you get the solution. So any question about homework number 4? So if you don't have any question on homework number 4, please let me know. And if you have a question, then also please let me know. Yes, you are right, Mr. Han. You are really correct. And yes, so previously you select the top point. So that was hard coded in your simulation code. So if you wanted to change the point for, how can I say, point for applying one, then you have to change your code. However, if you do this homework number 4, then just changing a text file for top contact, then you can immediately change your contact position. So that's quite good for your can say your use of written code. Let's say that now you are all of you in our classroom are developers, so they can actually change their own code because yes they have a certain right of permission and they can compile it. But in this case, if you have to distribute it to other guys and persuade him or her to use your own code, then what should you do? If you wanted to simulate this code, then please let me know. I can change my structure and my code, and that will be adapted to your structure. That is not possible. So you know that the Laplace equation is not very difficult to implement. However, by following this series of homework problems, we wanted to prepare a code which can just read the common text file format and can perform many different structures without changing its internal code. So yes, as you say, the difference between homework number 3 and homework number 4 is now we can solve, uh, the contact which is made of lines or edges. But another point is the position can be specified you. I mean that the user can ordinary user can change their own terminal specification. Mr. Han, is it enough for your question? And that was a really good question. So quite a natural question can be expected from our students. Okay, so uh, how about other two students, Mr. Park and Mr. Jung? So please leave your comments whether you have a question or no question. Yes, so since you have just 2 days for homework number 4, I will just give you very simple homework problem. So do not touch your, how can I say, main body of your simulation code, just to add certain capability to build your own terminal specification. So yeah, that's enough. Okay, thank you, Mr. Jung. So you don't have any question on homework number 4. Okay, good. Okay, so now I hope that you can all uh, solve this problem quite easily. So that will be the homework number 4, problem 1, and I'm just curious whether you have sufficient time to solve homework number 4's problem 2. The natural next step for our code development is now consider position dependent permittivity. So now we are no longer considering the Laplace equation. Laplace equation. Laplace equation is given by this form. However, from now on, we will consider the source-free Poisson equation. So source-free. Here, source means that the right-hand side of our equation. This part is typically called as a source term, and you know that source term is now vanishing in this case. So the general form of our Poisson equation, so-called Poisson equation, written with the electrostatic approximation would be looks like this. This is the form, the general form of Poisson equation. However, when you say source-free form of our Poisson equation, then we neglect this term. Yes, so of course this negative sign is also eliminated. Therefore, we will just consider the epsilon, which can be possibly a function of position, and yes, that is our next equation to be solved. Okay, so do you have any question about source-free Poisson equation? So if you are still curious about source-free Poisson equation, then I have prepared many previously recorded lectures or videos for this source-free Poisson equation. You can easily understand its meaning. So now let's go to this form. Yes, this is the form actually we have to use in our implementation. Of course, epsilon can be a function, but usually we in typical cases in computational electronics, usually this one is the general position like x, y, z. However, instead of that, we will just consider epsilon as a material property. So, if a certain position x, y, z is belonging to a certain region number 1, then epsilon at x, y, g will be actually the epsilon of region number 1. And if region number 1 has a certain material, so material number 1, then we will have the epsilon value of that material. So simply speaking, let's just think about this form. Yes, so this is oxide and silicon, and if we consider certain position here, then what will be the epsilon? That will be obviously the epsilon or permittivity of silicon. Also, if we consider a point here, then obviously we will have the epsilon of oxide. So that is really quite straightforward. So what I wanted to you is just to consider certain configuration. I mean that this is 7, 9, 10, 3 is the boundary for how can you say, boundary for our contact, so boundary for our two different regions. So say upper one is once again having the permittivity of oxide, and let's just say the lower part, lower region, has the permittivity of silicon. So now you can understand your element file will be a little changed. So now your element file, previously you don't have any information about region, but now they are different. For example, consider a triangle 6, 9, 7, and 7, 9, 8. Previously, they had the same property. So because as Mr. Pa previously asked me, quite obviously, there was no difference between these two triangles, because in Laplace equation every position is just, or every triangle are treated as equal. However, now you can easily understand the triangle 6, 9, 7 and a triangle 7, 9, 8 are belonging to two different regions. So one is silicon and one is oxide. So we have to consider different things. For example, let's say this one. Usually what we do is usually specify different in a different file. We have 6, 9, 7, 6, 5, 9, 5, 10, 9, 5, 4, 10, 4, 3, 10. That is enough to specify only lower region, so silicon region. And for upper one, we have to introduce another one, like 7, 9, 8, 9, 10, no, sorry, 9, 10, 8, and 10, 1, 8, 10, 2, 1, 10, 3, 2. So everybody, are you with me? So I just specify two different regions. One is specifying the lower one, which have silicon permittivity, and the upper one specify the upper region, which has the oxide permittivity. Of course, you have to introduce two separated description for them and read them sequentially and construct the whole system. So your vertex file is not altered. You know, vertex is just in this computational electronics. Usually, vertex is treated as a purely geometric quantity, so it does not have any information about material property. However, the element like a triangle, edge, or something, depending on the dimensionality of your system, that should be regarded as material dependent one. So you have to introduce two different, for example, two different files for two different regions, or just one one region, or one file. However, they are separated, so you can easily understand their differences. So I will not give you the how can I say, formally determined description about the file format. So usually, so yes, so you can invent your own file format, but in order to specify this file, you have to introduce these two different region specification. Whether that is inside one file or that should be separated into several files, that doesn't matter. But usually we prefer to have it in a one file. So then how can I do that? Well, the usual way is just to specify. Uh, the usual way is, for example, region name. It's a name, and it's a material property. And the number of elements, then the list of your elements. That is a typical way you do it. So in your element file, or in this case maybe you can have a different extensions, file name extensions, like region or something like that. Anyway, you can define in that way. So okay, so I don't have the firmly defined description about the problem, but anyway, I think that this is also a part of our lesson. As a developer, you can define or you can invent something. So please think about your own way to specify the system. So how about our students? So are you all with me about this structure description? So you can now build your own system or your own file format to describe certain structure. Of course, this is for just two, we can say, two region problem. However, in reality, we can define many different several regions. For example, if we consider typical MOSFET, planar MOSFET, then obviously we have to have oxide region, and yes, also we have silicon region. So if we divide it into in such a way, then that is so simple. You will have just two bulk regions, and after that you will have here and here and here and here for your context. That is enough for this planar MOSFET. However, even for this simple planar MOSFET, usually people can define certain different regions, and let's say that this is called a region called substrate, and this one is called as a source, and this one is called as a drain. Yes, in this case, even for this simple structure, we can define multiple. The number is much larger than number 2. Okay, 1, 2, 3, 4. 4 bulk regions can be generated quite easily. Of course, you can generate it even further. I think that maybe Mr. Park knows it quite well because his real research, master research topic is quite much related with generating certain device structure. So anyway, if you have this multiple regions in your uh, device, then you can specify just to concatenate all of this region specification to one. The region first region is specified. After that, your description for second region is just attach and attach it and attach it. For example, this is for oxide region, and this is source region, and this is a silicon substrate region and drain region. Then that will fully specify your complicated system. So, so usually, right, that is not a mandatory one, but usually people try to build just one file specifying all regions inside your device. Okay, so I wanted to ask to our students about any question for this file format or specifying multi-region structure. Okay, could you please show you your opinion? Show me your opinion. Thank you, Mr. Jong. How about our other students, Mr. Park and Mr. Han? Okay, thank you, Mr. Park. Okay, so thank you. And yes, so but I think that we have to one issue for this simple system. Even for this simple system, we can immediately have certain question. Oh, now by specifying these elements, now we say that okay, this is, and this is, and this is, and this is belonging to a region 1, and by specifying another region, now we understand this one, this one, this one, this one, this one is now belonging to the second region. This is quite good. But my question is, we are now asked to ourselves about the interface between two regions. So here we have an edge or a set of edge, say that 7, 9, 9, 10, 10, 3. These three edges are constructing an interface between our silicon region and oxide region. But up to now, we have not discussed about the interface. Then how can you specify the interface in this case? How about your opinion? So once again, I wanted to ask all of our students your opinion. How can we specify the interface? There is no, how can I say, no golden answer. So everybody can freely show one's opinion. So how can you specify the interface? Could you please leave your opinion? So how can we specify the interface between two regions? Previously we had no region. I mean that just one single region. So there was no interface. However, since we consider now multiple regions inside our system, obviously we will have several interfaces. Then how can you specify the interface or the interfaces in our structure description? How about your opinion? So So there is no golden answer. Okay. So Mr. Han, okay. So then Mr. Han, your opinion is okay, okay. Mr. Park, thank you, and Mr. Han, thank you. Internal point and okay. So I think that in the case of Mr. Han, we have to uh, give a counter example. Okay, that is a really good trial, but think about this way. Mm. Thank you for your quite interesting. Why don't we consider a system like this? So now in this case we have region boundary like this, and we have several triangles. Yes, so almost close to the structured one. Yes. And say think about this one. Then if we follow Mr. Han's approach, then we can specify connecting the internal point and boundary point. Means that, for example, certainly this is a boundary point and this is certainly an internal point. So the edge connecting them, for example here, this guy satisfies his suggestion. However, you know that this is not, yes, this is not the interface. obviously the interface should be, yes, so interface should be shown here, and yes, we have to find out a way to determine these edges. And so how about Mr. Park? In your case, um, okay, so you are now talking about the calculation method. However, the specification, I mean that when you share your structure information with your friends or your colleague, how can you do that? So that was my question. And okay, so in the case of Mr. Chang, so the absolute position of interface is specified in following your um, strategy. Okay, thank you for your quite interesting uh, answers. Yes, that is quite reasonable, all of them. Oh, but my answer is but first of all, I have to say that this is not the golden answer. So I just introduce the typical way where people are doing in reality. So if your method is reasonable enough, then you can do what you wanted to do. But I wanted to say typically, my answer is interfaces are not explicitly specified. That is my answer. I mean that obviously this yellow line, the interface, this interface information is really important when you calculate the Laplace equation or not Laplace equation but Poisson equation. But thing is, when you specify or when you describe your structure with a certain file format, usually interfaces are not explicitly specified. Then what happens? Based upon the information you have, you just build one region and two regions. Then this interface should be constructed by the device simulation code. Usually, the structure description file does not contain the information about the interfaces. Then, by collecting your vertex information or for example, element information and try to find out the how can I say try to find out the intersecting edges, then you can find the interface quite naturally. So my answer to your my response to your answers is three answers or three opinions are quite interesting, but in reality, interfaces are not explicitly specified. That is my answer. Then, once again, the natural question is then if interface information is not explicitly provided, then how I should calculate it? That is one thing. But that is closely related with the Poisson equation. For example, let's say that I ask you to solve the Poisson equation for this system, then how can you do that? Or if I ask you, please try to find out the interface, then what will be your strategy? You have full information about elements, but yes, you have to find out the interface. In this case, what we can do is, you know the information of every element, and from this element information you can find out three different edges, because your element is a triangle, so you always have three edges, and also you have three edges, and also you have three edges. Then now you can list, how can I say, you can list all edges. Yes, from these blue regions you can make a global list of your edges. Also, yes, also you can select, or you can generate a list of edges from this lower region. After that, you can just make the intersection between two set of edges, and then you will have a much shorter, you can have a much shorter list for your regions or your interface edges. Then that will be the interface edges will be the information for you. Okay, so sounds quite straightforward. However, you have to be a little bit more careful about that. For example, think about this one. Let's say that this is vertex number 1, vertex number 2, and this is 3 and 4. Then let's consider magnified view on this small piece. Yes, and now yes, and obviously we will have the interface. So now you understand, we are now talking about the, say, the magnified view around these two triangles. So now let's say the vertex numbers are given in this way: 1, 2, 3, 4. Then from this upper region you will have the specification like 1, 2, 3. Why do you have such kind of thing? Because you usually adopt the right-handed rule. So your triangle specification will be 1, 2, 3, or 2, 3, 1, or what? 3, 1, 2. And also for this lower part, lower triangle, you will have 1, 4, 2, or 4, 2, 1, or 2, 1, 4. Yes, you will have, anyway, you will have this description for these two triangles, and from them you can extract edge information, edges, and you can generate edges. So any of them will generate something like this: 1, 2, 2, 3, 3, 1. also it will generate 1 4 4 2 2 1. Then let's try to make the intersection between these two edges, or two sets of edges. So here we have one set, and here we have another set. So when we make the intersection, then what will be the answer? Of course, the answer should be 1 2 or 2 1. The question is, oh, they are the same. The edge connecting vertex 1 and 2, or the edge connecting vertex 2 and 1. Oh, they are same, but they are aligned in different way. So we have to, how can I say, when we make an intersection, we have to treat them as equivalent description. So do you have any question about my question on when you make the intersection? So please respond. So whether you have any question on it or not. So then if you don't have further questions, then I wanted to wrap up today's lecture with the second homework, second problem of homework number 4. So we have two problems, but none of them are difficult, so you can do it quite easily. Okay. So if you don't have any question, then please say so. Then I can proceed with our homework assignment. Okay, thank you, Mr. Han. Yes, interface intersection means that so the step is you have triangles. Yes, you have triangles for your first region, and you have triangles for your second region. Then from them you can also generate edges and this type of edges and edges. So Mr. Han, so are you with me up to here? You can extract the edge information or edges inside your region. So this is region number 1, and this is region number 2, and you can extract the edge information. Of course, you can have many different, how can I say, different triangles, and each triangle can give you each triangle give you 3 edges, and for example, if you have another triangle, and this third triangle will also contribute the edge, like connecting 1 and 3. So anyway, you can have a list of edges and they can have duplicated information. For example, if we just follow this way and that way, quite naturally the edge extracted from our triangles is just 1 3 or 3 1. So if we follow this way, then this triangle will contribute to 3 1, and if we follow this way, then this triangle will contribute to 1 3. They are duplicated, and you wanted to treat them as a single description. So yes, now you have certain edge information, list of edges, and please compare them. For example, yes, let's say that 1 3 and 3 1 are duplicated and just treated as one single entity. So now you say that I have 1 3. Do you have, do you means that you means that region 2? Then I have 1 3. You guys have 1 3, and if the answer is no, I don't have 1 3, then 1 3 is not on interface edge. However, if it asks 1 2, then what will happen? Do you have 1 2? Yes, I have 1 2. Then yes, this 1 2, the edge connecting vertex number 1 and 2 is belonging to interface. Okay, so Mr. Han, I'm not quite sure my answer is so clear to understand you or convince you, but could you please give me your feedback on my uh, explanation? So if you have further questions, please give me your further questions. And how about Mr. Chong and Mr. Park? Do you guys have any question on this procedure? So if you don't have any question, then please let me know. Then I can just announce homework number 2, or I mean that the problem number 2 of homework number 4. Then I can wrap up today's lecture. Okay, Mr. Jong. Oh, uh-huh. Oh, yes. So that is quite interesting question. So let me just do it. Here, let's repeat this structure, this example structure once again. When you read the information about the uh, lower part, then you will say that 6, 9, 7 in your mind. So you will have something like this. When your first region loading is over 4. So Mr. Jung, after leading your first region, then in your system you have the information like this. And that will be assigned to a silicon material. Oh, this is a silicon. So Mr. Jung, are you with me? So could you please let me know? So when we read the first region, then we will have just information about the first region. And the position 7, 6, 9, 5, all over their, how can I say, absolute positions are specified in our vertex file. So exact position 7, what is it? That is found in our vertex file. So Mr. Jung, are you with me up to here? So if you can understand up to here, then I can proceed my answer. Mr. Park, yes, you are right. So region is considered as a set of elements. Okay, so thank you, Mr. Jung. So now you have loaded the region 1, and now you can load your second region. So 7, 9, 8, 1, 10, or what is it? 1, 7, 8. Oh, yes. Anyway, so sorry about my ugly drawing, but anyway, now you can understand what is going on here. Okay, so when you read the second region without bordering, without being bordered by the first one, you can independently read the second region. So when you read this second region, no information about this first region is required. You can just read the second region without any interruption from uh, your first region. So, Mr. Jung, so you understand that they are independent. Up to now, they can be loaded independent. Okay, that's good, but since they are loaded separately, they don't know oxide region and silicon regions are attached. So we have no idea where these two how can I say, regions are connecting to each other or just disjoint. So they are not connecting to each other. We have no information about that. Only when we realize that this H, this H, and this H, or this H, this H, this H are shared between region 1 and region 2, then we can realize that, oh, they are connecting to each other. So when I come back to Mr. Chung's original question, uh, when we build a region itself, individual region can be independently constructed. The only missing information is whether these two regions are attached to each other or just disjoint. That information is missing in this part. So when you just load the region information independently, so that part is actually done by your code, the device simulation code. And in order to calculate whether they are attached or not, you have to find out the intersection of edges, and that is done in this procedure. Okay, so Mr. Jung, so I'm not still sure about my answer is quite enough for your question. So if you have further questions, then please let me know. your question is quite important, and so if you have a further question, please let me know. I can happily answer to your question. So thank you for your active participation. Then now then I wanted to announce our second homework problem and finish this lecture today. Okay, second lecture is not related with Poisson equation or Laplace equation, just finding out the interface. So the desired structure is once again the circle. So please use the circle you have used in your previous homework number 3. So you don't have to reinvent anything. So previously that circle was fully filled with a certain uniform material, but now introduce a region like this. It looks like this. Think about this one, and yes, obviously that will be the interface. So my question or the homework number 2 is, please write down a code which can read your own file format specifying these two, how can I say, these two regions, and automatically calculate the intersection, so the interface. That is my second problem. Okay, in this time you don't have to calculate any quantity, means that numerical calculation is not required, just to visualize it and yes, find out the interface. Quite easy. So you can easily expect that later you will be asked to solve a certain equation on this domain. However, right now you can just visualize it and also find out the interface. That is enough for your homework number 4, problem 2. Okay, so do you have any question on homework number 2? So please let me know if you have any question on problem 2 or problem 1, and if you don't have any question, also let me know, then I can wrap up this session. Just to make a structure. This is your goal. So if I remember correctly, you have already done a circle, and its visualization was in homework number 3. But now you introduce same circle divided into 2 different regions. So you have to write down your own element file. So change the format of your element file to specify silicon oxide region and silicon region and visualize it. Finally, calculate the etch information out of this silicon and oxide region. So, Mr. Han, is it enough for your question, or if you have further question or further uncertainty about this homework number 2, please let me know. Okay, thank you, and thank you our three students for your active participation in this session, and your questions are really interesting and sometimes quite insightful. Thank you, and okay, we have really short time to prepare homework number 4. However, homework number 4 is not that difficult. So please finish and submit your homework within the schedule, and let's make the next session on this Thursday. Okay, thank you and see you. Bye.